Good morning, ladies and gentlemen. Welcome back. Today's Wednesday, October the 14th. And as you can see, you can read here what we're doing about the information. But today's lesson is on domain and range again. We're going to look at domain and range. A lot of you know that. We talked about what are general 5 base functions, and you should know them. And the key thing is if you can graph the functions, ladies and gentlemen, if you can graph them, technically, we should be able to ask you domain and range, right? However, let's take a look at example 1. If you take a look at example 1 from the package, it clearly says they're linear, right? And the first one, y equals 2x minus 5, this is super easy. Right? There are no boundaries or intervals that we have to worry about. So a lot of you actually know the answer intuitively, even if you don't know what the graph looks like. But almost, and I say this carefully, almost all straight lines, their domain is x belongs to all real numbers. Right? Almost all, right? That's really easy. It's basically from negative infinity to positive infinity. It goes all the way if we're talking about straight lines. How about the range? I think everyone agrees it is also y belongs to L. So the linear ones, they're a little silly. But if you can graph this, you should be okay. In fact, I will graph this as a sketch, even though you don't have to. The slope of this line is rising 2 over 1, and the y-intercept is negative 5. And I was just talking to my friends online with some gaming. Negative 5 is maybe down here, and as a sketch, like that. So just to reconfirm the domain and range, it's continuous, there's no breaks. I think everyone's okay, right? Really easy. Notice, it probably has an x-intercept, but who cares? Who cares, right? Doesn't matter. We're gonna skip question B. I'll just let you guys figure that yourself, or you can look at the PowerPoint. A lot of you know the answer for question B, and you can just check online to see it. But question C, this is a special line. In fact, the equation of this line, some of you, when you wrote the test, were asking me what's an equation. This is an equation, right? In fact, a lot of you should innately know what this is. So notice, I'm already going to answer the domain for this. X belongs to real numbers. But the range, it's not going to be y belongs to real numbers. Any volunteer want to tell me what the range is? This is really easy. Hi, Saba.
X equals 4.
Not x, it's y.
Oh, sorry, y equals 4.
Y equals 4, such that y belongs to 4. It is that value. And again, this graph, if you can see it, I'll move the screen over at 4. It's that value, right? So although the domain is all real numbers, there's no slope, right? So technically you don't need that. So that is the range. For straight lines, you have to be careful. Any questions about linear straight lines? Any questions? Let's erase this. Example 2. A lot of you already know they're actually graphed for you down below, so I wouldn't cheat. I wouldn't look down below. Well, let's do the first example. Y equals 2. 2 bracket x minus 3 squared plus 6. A lot of you already recognize this as vertex form. To talk about in terms of connect to our transformation unit, vertical stretch by a factor of 2, horizontal shift right 3 units, vertical shift up 6 units, right? So what would be the domain for this? Really easy. This is always true. And again, if there's any conditions though, if there's any conditions that restrict the domain, but this one is almost always domain belongs to all real numbers. The way that you can think of it, and you input any value for x, it should output you an answer, right? Conversely, the range though is related, that's why vertex form is really, really powerful. It's related to the vertex, in this case 3 and 6, but as well, the direction of how the parabola opens, right? So I apologize for some of you, you might have to memorize this, but this definitely is a vertical stretch, it's opening up. So in this case, we're going to talk about the optimal value, or in this case, the y coordinate of the vertex. So y is greater than or equal to 6. Again, visually, a lot of you already know what this looks like at 3 and at 6. Looks like that. And that's why we did this already on our quadratic unit test. How many real roots you can determine? That's vertex form is really, really powerful because when A and Q are opposite signs, it has 2 real roots, but when they're the same signs, there's no real roots. Right? So a lot of you already know that. So question, example B, C, and D, you could probably figure it out on your own. Okay, so that's the domain and range for quadratics. We'll turn the page over. And notice, there's a lot of graphs. So let's just do example 3 over here. And this time, let's just pick one of the answers, or one of the questions. Let's try question, example 3C. And again, I'll move this over. My apologies, Maria. Example 3C, notice I'm giving you as an equation, and that's kind of what we're doing. So a lot of you realize you can definitely use, if you were doing this on an assignment, although I encourage you to try to do it yourself, but you can always check by using Desmos or GeoGebra, so you have a better understanding what the image looks like. But sometimes we don't have it, and we'll explain that in a moment. One more time, this is obviously a cubic function, so it's going to be an A value reflect across the x-axis, and vertical compression by a factor of a half, but then shifting up 2 units. So in this case, and now notice, hopefully as I'm slowing down, for straight line, the straight lines and quadratics, for sure you should be able to give me domain and range. For almost all of us in grade 11, we tend to teach only just domain for this one. So for this one, x belongs to all those numbers. Again, there's no conditions that are changing this. The range, this is tougher. Okay, so this is where I'm going to pause. And this one I would recommend, if we can graph it, then you should be able to tell me the range as well. In this case, I think everyone's okay. We have a cubic that is at 2. Something like that. And it looks kind of vertically compressed, so maybe it looks something fatter, whatever. I'm exaggerating, obviously, right? And you can see that there is a graph there. So the range actually is also y belongs to the numbers. Because you can see it, that there is no breaks or any discontinuities. We're going to skip the radical one, even though I wanted to do it, because I think we talked about it online in the synchro class. But I think you can manage, and the absolute value and the domain and range. So those examples, notice the graphs below are provided for you, and if you can graph it, or if you know what they look like, you should be able to solve it. Okay. The hard part for this lesson, though, if you take a look at some of these examples in your exercises on page 5, notice there's no images here. So let's take a look at one of the questions. Let's just do one of the exercise questions. And that's why we teach you all the base functions, and that's why there's infinite functions to worry about. Let's just take, I don't know, question 10. So this is for the exercises. And hopefully I'm going to get this right. Y is equal to 1 over x minus 4. So clearly this is not a quadratic, this is clearly not a cubic, clearly not a root function, nor absolute, it's probably the reciprocal function, right? And if I were to ask you, what does this look like? It's probably a horizontal shift right 4 units. So if I were to sketch this out, at 4, notice what I'm doing, I tend to teach it this way. That is going to be where our asymptotes are. X is equal to 4, that's the vertical asymptote, and y is equal to 0 is the horizontal asymptote. And then I'm just sketching, so I'm not even using the table of values, but that's how the image looks like. So once you can see that image, you should be able to give me domain and range for this. Any volunteer want to try? Again, you can cheat by looking at the answer, and hopefully we're going to get this right. We had a guess, ladies and gentlemen, at home, but I don't know. Eric!
Isn't it like both of them, like y is this a part of a rational number, but like ydr, but it can't equal 0.
Cool, so let's do the domain. So the domain for this, it's any real number, except, oh, really? Yeah, x can't equal to 4, such that x can equal to 4. You can do it this way, right? So it is all real numbers. It's continuous. But at 4, I have to lift up my chalk to continue, and it keeps on going. But at 4, that's the restriction, nice. And for the range, now you're going upwards and downwards. Maria, you wanna try?
Y, any real number where y cannot equal to 0.
And that's why a lot of you realize, thank you, these are actually the restrictions or the asymptotes. Okay? Again, one more time, ladies and gentlemen. Normally, if we graph, or normally I only ask for domain. Okay? Excuse me. So we're going to move on to the optional worksheet now. And this is a little bit more of the enrichment, ladies and gentlemen, at home. If you're not too sure, we're at domain and range of advanced functions, optional. And we're just going to do 2 of the examples. And some of you, seriously, also in class, you might need to look at the PowerPoint at home. Like, I'm not going to make it so brutal for you, because these are tough. Okay? So, let's just read it out really quickly as a refresher. Domain, all possible values of x, the set of the first elements in a relation. Range, all possible values of y within the domain, and the set of the second elements in a relation. So the first example we have is this one. And it says solve for x squared minus 16 is greater than 0. Find the, so this is why we're doing it. Now, this is your first time seeing now an inequality with the quadratic, right? So a big hit, and if you follow the PowerPoint, I mean, it is an inequality. You can definitely do it as an inequality, but the tip for what we're going to show you, you treat it like an equation. Everyone okay? So treat it like an equation. So treat it like this, even though we are going to interchange this in a moment. And don't get me wrong, I will show you what the graph looks like. A lot of you already know what the graph looks like, and hopefully you actually understand what this is. When we solve this, add 16 to both sides, square both sides, you get plus or minus 4, right? That's the solution if it was equal. Everyone agree? That seems super easy. However, visually, just to show you what this graph looks like, if we took y is equal to x squared minus 16, a lot of you actually understand this. We want the function that's greater than 0, right? And this is actually important. A lot of you actually, I think, understand this. Where is the region of space that is greater than 0 in the context of domain? Well, it seems to be from here onward, this is positive, and from here onward, this is positive. Everyone see that? So we just need to know what these 2 points are. But a lot of you already know that these are called the roots. And so I think a lot of you actually innately know what this point is and know what this one. This one's negative 4, and this positive 4. So we're talking about this region of space and this region of space. So to show you as an alternate way of doing it, notice I'm going to treat it like an inequality. Notice add 16 to both sides, nothing changes. The only effect is when we're multiplying by negative. This one's going to be weird, right? When we square both sides, we get this plus or minus 4. If this doesn't make sense, we'll talk about this more. Notice, that's why I'm trying to show you this. The math this seems right. On a number line, for the domain, when x is greater than 4, that kind of makes sense. And where does that align with our graph? I think everyone agrees it's this side. You see that? But this, if we say x is greater than negative 4, watch what I'm going to do in blue chalk. At negative 4, that doesn't make sense. You can clearly see between negative 4 and 4, negative 4 and 4, it can't go this way, right? Everyone see that? So this is, don't get me wrong, this is incorrect, right? So a lot of you already know that this is actually this portion. And so what I'm trying to share with you, ladies and gentlemen, just something to problem solve. Some students actually, and if you go to Khan Academy, they do what's called a sign chart. I'll write that down. Sign chart. And you'll be doing this a bit more in grade 12. I'm just trying to show you, you can almost kind of do a check to see if this is true. And I wish we had more time to explore this. Just for the domain, right? Just for the domain. Notice the interesting portion of this is between -4, or let's just do it really quickly. Negative infinity to -4. -4, I'll do it as the internal notation. Between -4 and 4, and then 4 to infinity. Again, this is called a sign chart. And all I want to know, what is positive, what is negative. And notice, in this context, this question says, the quadratic is greater than 0, right? So we're interested in only in the positive regions. And if we try some numbers, let's say, what's a number that's less than -4? Well, -5, right? Over here, -5. And if you plug in -5 into the original question, -5 all squared, 25, 25 minus 16, who cares what the answer is? But that's a positive answer. Everyone agree? So that's positive. How about we choose a number between -4 and +4? Well, an easy number. You could say -3. How about 0? 0 is in between there, right? And if you plug in 0 here, 0 squared is -16. -16 is not greater than 0. So that's negative. That's not true. And I think everyone agrees what we're doing. So the answer for this question, and that's why I'm trying to show you in a couple of ways to confuse you just a little bit. A lot of you realize if we have the function, if we can graph it, and understanding what this means, I just want that region of space that's less than -4 and 4. So notice the correct answer for this, the domain is x is less than -4, comma, x is greater than 4. Or if you want to use the equal notation, right? Does that make sense for the domain? Flora.
Can we also understand it this way because we added another negative sign, so we have to flip this sign?
Yeah, so I'm just trying to say, like, that's where the similarities kind of end, right? That's why you should be suspicious when you see something like this with the inequality. That's why I'm just trying to point it. Yeah, we have to flip it, even though we didn't talk about rules about squaring, right? It's only with multiplying divided by negatives that we flip the sign. But this one, I'm trying to show we should be checking our scenario. And this is the same thing that in the prior class, ladies and gentlemen, at home, someone was asking about absolute value. This is what we're kind of dealing with, our cases. There's cases that determine whether or not it's going to be true. Okay, so I just wanted to show you this quadratic way. I'll be honest with you, that's why it's not on our test this year, and you're going to do a lot more of these with scenarios. Okay, so I like this first example, example 1, and I want you to try it for yourself, example B, and again, you can always look online to that question. Okay. Any question about this example 1? And notice I didn't do range. But do you want me to do range? I don't think we need to do range. The range is obviously related to the vertex, right? So for the range for this, y is greater than -16, right?
Is it like greater and equal to -16?
Shoot, I gotta double check that. I have to look at my notes again. See, normally in grade 11, I only ask for domain. Maybe it is. I have to double check. Maybe when we check the PowerPoint, I might be wrong. Let me double check. I think it's the same. Because it's only asked for, the inequality is only not completely equal to. Great.
Can you explain the sign chart thing?
So what I chose, notice I got the -4, how I got these 4s, I actually solved it, right? I treated it like an equation. And so what I'm trying to share with you, ladies and gentlemen, like you're not gonna check, like unlike a table of values, we're not gonna check all possible values. We're not gonna try -7, -6, -5. Like, what's interesting for us, Grace, is that we're interested in -4 and 4. And so what I'm trying to share with you, what you're doing is some simple algebra to plug back into the equation. So for example, in this case, I can't choose 4 because it's one of the roots, right? But we just want it to be, like if it was actually 4, this would be 0, and 0 is not greater than 0, right? So we can't include it. But maybe choose a number that's greater than 4. So let's try 5. If we plug 5 into this will then become a true statement. And so I'm trying to show you the sign chart helps us determine the domain, and I'm also trying to reinforce it visually. And notice I shouldn't really circle the -4. I really should like kind of done this, right line, basically. It should be there should be a hole here, right? Because I'm not supposed to include 4 or -4 because of this inequality.
So what is the plus in the dash? Is that a dash or is that a?
It's a negative. It's like it's incorrect.
Oh, okay.
It's negative. Whereas let's just say this is what argument's sake. We change that to negative, then this would be correct. This would be true. This is the region of space we want, and not those two. So the answer is the domain would be -4 and 4. Right? So it's the opposite, right? Does that make sense? So the sign chart helps us to figure out where the regions are positive or negative to make the condition. Okay? And that's why inequalities are. So there's a couple things that we're doing. But it's a good question. Stop very quickly.
Why is the vertex -16? Would you have to like factor it and get the of the vertex? And
This is also in vertex form. So if you treat it like y equals x² minus 16.
Oh, it's in vertex form?
Yeah, or
We wouldn't be able to tell because
sorry.
we wouldn't be able to tell because there's no key.
Okay, so now you can see it.
Okay. So do
Right.
you just assume it's in vertex form?
Sorry.
You just assume?
No, but if you need to put this like this so that you can see that is 0, -16. Right? If we plug in, so if we treat it like this, we plug in 0 for x, that's gonna be -16. That is, and that's why you also know is if the quadratic shifted down 16 units, so they're all connected, right? So if you can graph it, you should be able to determine domain and range. The hard part, what we're trying to do is, let's put this back, is the inequality. That's what I'm just trying to show. And that's why some of you say, that's why I'm trying to appeal to, the graphing is actually, or the sketch for this is very helpful. You can almost determine if it makes sense. The only hard part is, do I really know what those values are? So you might have to do some algebra. So I really wanted to try example 2, but I don't think we have time for example 2, so that's okay. So I just want to show you a couple other scenarios now. I know what I can do. I'm just going to say the main of functions here. So these 3, they're done in the package and they're done on the PowerPoints, but I asked you to copy these down, and we're going to kind of do these only. And so where I'm going to find the domain of these functions. And don't get me wrong, if you can still graph them, ladies and gentlemen, that's great. But I'm trying to show you, this lesson was actually in the old package, or in the old function unit, when we introduced domain and range. And at that time, the students did not know what the graphs look like. So you have something slightly at your advantage that you can determine what these graphs look like. But I'm going to pretend we don't know what they are, and we're just going to look at the functions. So let's say we want the domain of these functions, and I'm going to give 4 examples. The first one is going to be this one. And don't get me wrong, a lot of you already know this is clearly a root function. This is probably a k value, and this is related to p, but we have to probably factor it out, right? So I'm making this up, okay? They're not in your package, so you might have to copy these examples out. So, and the lesson that we connected with radicals, a lot of you realize we can't take the square root of a negative number. Now, technically we can, but the answer would be a complex number, and we can't graph that, right? So to find the domain for this, really, really easy, and notice it's a radical. You basically take what's under the radicand sign, and you make it greater than or equal to 0. Right? A lot of you realize we can only really evaluate positive expressions in here. Right? So to find the domain for this, we're going to do some algebra, and this one's relatively easy. 2x plus 6 is greater than or equal to 0. To refresh your memory, we start isolating for x. 2x is greater than or equal to -6. Divide both sides by 2. X is greater than or equal to -3. And that's the domain. Of course, a lot of you know from our unit, if we were to do it this way, it's a horizontal compression by a factor of a half, and a horizontal shift 3 units left. So it's going to look something like this at -3, correct? And that's the domain. And notice how I'm writing it, it's going towards right. So that's why a lot of you say, well, why would I bother doing this? I'm just trying to show you from the equations, you can do it. But if you can graph it, domain and range, you can solve. Now notice, I'm not going to do the range for this, I'm only going to do domain. Danielle.
So do you always put it as greater than 0?
Is correct for when it's written like this. And we'll do a summary in a moment because I'm going to try to confuse you. Good. So that's our first example that I'm trying to teach you. Our second example, I think a lot of you know what I'm going to be doing. Again, we haven't really seen this graph because we've only been doing we've only done reciprocal linear functions, but this is a quadratic. But some of you understand there's a connection between this and our rational expressions unit. Any volunteer have an idea of what we can do for this? Just, you don't have to give me the answer, just strategize the technique. Anybody? Bridget?
Do the factor and then do the restriction?
Beautifully said. Now, we would factor first, right? So I think everyone's okay. X plus 5 times x minus 1. Hope I factored that correctly. And again, notice what I'm trying to show you, the whole connection of what we're learning as. What's the restrictions for this? Right?
X cannot equal -5, and x cannot equal 1.
That's correct. So I'm going to be honest with you, I actually don't know what this quadratic reciprocal function looks like, but I do know at -5 and I do know at 1, there's some holes or at least some asymptotes that are causing some problems. I don't know what the image is going to look like, so maybe it looks like this, maybe it looks like that. I don't know. I could be totally wrong. I don't know. Because that's the whole point. That's why I'm trying to show you. So from this one, notice it's what Bridget said, it's the restrictions. And Maria actually helped us out with those answers. Notice our last one. And this is what Danielle, I think, was asking. This one we're going to get at. Our last example, well, and I'll number them again. Y equals 1 over the square root of x minus 5. Now this one, I do not think we've even talked about how to graph, so we're not even going to graph it. So to illustrate this one, this is kind of a combination of this example and this one. Everyone agree? It's kind of a combination, right? Because the square root is in the denominator of our reciprocal function and everything. Slowly, some of you I think are interested in what these look like, and that's why, again, with Desmos or with GeoGebra, you can find and see what those functions are. So let's talk about it good. If we take a look at the square root, notice we can still do the same idea. X minus 5 is greater than or equal to 0. Because again, let me understand, the square root of 0 is 0. That is an answer, right? You hand in an empty test, you get 0 marks, right? That's an answer. But a lot of you realize, if we were to do that, we would have 1 over 0, like if we solve this. So the answer for this question, and I'll emphasize this in yellow chalk, and that's what I'm trying to show you, we just make it greater than 0. Because now with this inequality that we solve, the domain is going to be x is greater than 5. And it does not include at that value of 5. If x was ever 5, don't get me wrong, that's fine for the radical component. But if it was ever equal to 5 for the whole reciprocal function, it would be a problem. It would have to be greater than 5. So 5.1 or 5.0001. And so notice with these 3 examples, they're a continuation of domain. Notice range is actually harder. And I wanted to show you with the example, but that's fine. Okay, so let's just label these examples. think you guys are okay. Any questions about domain and range? If you can graph it though, technically I should be able to ask. 7.
What do you do for the range then? Do you just graph it and find out?
So for this one, though I'm not gonna ask you, what's the range for this? I think you can clearly see.
X
It's
is greater than.
Y, range is always 1. Y is greater than or equal to 0, right? Because it's moving more positive, right? Everyone okay? And that's why you kind of cannot ever forget domain and range, and that's why, in some sense, this is actually a better synergy of what we've been doing. Supposedly, again, someone was asking, what time of the course is this usually? This is roughly around January. It's not January. Grace, you had a quick question?
Is the sign chart optional?
The sign chart is only what we did for the inequalities, and it is optional. It's just a technique that I'm trying to show you that is very helpful. And you hopefully, so if you see the PowerPoint, you might find it confusing, like what's going on? Why are these charts here? But it's a technique that we show you in advanced functions. So hopefully, it's like none of you, hopefully when you're at home, ladies and gentlemen, none of you can complain, Mr. Chen didn't teach us this. Like at least, oh, that's what Mr. Chen was talking about. So when you get Mr. Petal or Mr. Gardner or Ms. Miron in grade 12 advanced functions, it is slowly, oh. Okay, so it is optional. It's just to help me to reinforce what I'm trying to show you. And just like Sab was asking, I want to really show you the example too, but we'll do that another time.